Okay, in this video I'm going to discuss three different ways that we can go about solving a reaction system. And we've already worked two of them before, but I want to introduce a new way of going about solving this. So let's just first review the various ways that we've worked with so far to solve a reaction system, or to go about analyzing it. So here I've set up this system where we have a reactor and we have 100 moles coming in, and we have the mole fractions of species A and B, and it reacts according to this reaction here, A plus 2B going to C, and we're asked to find out the outlet compositions. We may be, for instance, given a fractional conversion of one of the species, or we may be given other information about one of the outlet streams coming out here, and we can use this to calculate what's coming out of the reactor. So let's just review the various techniques. First one is, number one, is a molecular balance. And we have done this before where we've written out our balance equations for different species. So in this case, let's just write out a material balance equation for A. Na out plus N consume is equal to Na in. And so that's our material balance, and in this case A is consumed because it is a reactant. If we know what the consumption is, or how much of it's consumed, we can just go ahead and solve for Na out. And let's just assume that N consumed is equal to 5 mole. So if we go ahead and plug in our numbers, Na out is equal to 20 mole. And that's just taking, again, NaN, which is 100 times 0.25, which is 25 moles. So 25 moles minus 5 moles gives us 20 moles. And then from here, we can go ahead and calculate NB out plus N consumed B equals NB in. Well, since we know how much A is consumed, we can calculate how much is B is consumed. So N consume B is equal to N consume A multiplied by the stoichiometric ratio. In that case, mole of A, 2 moles B. So the amount of consumed B is simply going to be this number here, 5 moles multiplied by 2, which is going to be equal to 10 moles. So that's how much B is consumed, and then we can go ahead and plug it into the material balance equation here. We can also go ahead and write out our equation for the material balance for C. Just shrink these down, move them aside, and we can write N consume, or actually in this case generated, since C is a product, got to remember the difference between consumption and generation, but N generation of C is going to be equal to N consume A, how much A is consumed by the reaction, multiplied by the stoichiometric ratio, and that's 1 mole C to 1 mole A. So that is equal to 5 moles. And 5 moles, since we didn't have any inlet in the stream, the amount of C leaving the reactor would be simply 5 moles. And that's the idea behind the molecular balance equations. We write out these equations whether a species is consumed or generated, and if we know how much is consumed or generated of another species, we use the stoichiometric ratio to calculate the consumption or generation of other species. So that's the first method, molecular balance. So let me go through the second method, and that's extent. So extent is very similar to the previous method, except the equations are slightly different. So in this case, Na out is equal to Na in plus stoichiometric coefficient times the extent. And in this case, A is -1, since 1 is the stoichiometric number up here, and A is a reactant. And NB out is equal to NB in minus 2 times the extent, because there's a 2 right up here, so it's minus 2 there. And then finally, NC out is equal to NC in plus the extent. And this is basically the equations we have set up. We set up our outlets and inlets in terms of extent, and if once we solve for extent, for instance, if we know the inlet and outlet of A, we can solve for what extent is and then apply that to these equations to find out how much B and C are leaving. So the key to the extent method is simply calculating or identifying what extent is, and then once you know it, apply that to the other species to get their amounts coming out of the reactor. Alright, let's talk about one more method. So the last method I'm going to be talking about today is atomic balance method. And this is slightly different than the previous two methods. Both of the previous two methods are based on molecules coming into and leaving a reactor and how much of those molecular species react. Atomic balance takes a different approach, and what it does is it uses balances on atoms themselves. So for instance, we assume that, let's just say we have a molecule H2O, and it's reacting to form H2 plus O2. And we need to balance this, so this will just put a 1/2 there. So here's our reaction. We're just breaking apart water into a reactor. Well, this type of atomic balance approach says that the H in is equal to H out. So all of the hydrogen atoms coming in the form of water are all the same add up to the amount of hydrogen atoms leaving the system, whether that be in hydrogen or maybe some unreacted H2O that may be coming out of a reactor. So the atomic balance says H in is equal to H out. And this holds for, this is just conservation of mass. Reactions, the molecular species change, but the atomic species don't change. If you want to look at atoms changing into other atoms, that's nuclear engineering, that's nuclear reactors. That's not what we're going to be talking about in this course. The other balance we would write here would be oxygen in is equal to oxygen out. So the amount of oxygen atoms coming in, again, oxygen atoms could be in water or oxygen atoms could be in O2, but the sum total of all the oxygen atoms coming into the reactor equals the sum of all the oxygen atoms leaving the reactor. And we can use material balances or set up our balances on atoms. So for instance, let's just assume we have 100 moles of H2O inlet. So the total number of moles coming into the system, number of moles of oxygen coming into the system, so we're going to write this NO in is equal to 100 moles H2O, that's what's coming in. Then we have to multiply this by the ratios of oxygen, the stoichiometric ratios. In this case, we're referring to the stoichiometric ratio of how much oxygen there is per molecule. So in this case, it's 1 mole H2O gives us 1 mole O. So the amount of oxygen atoms coming into there is equal to 100 mole. And that's basically what we do here. If we have, for instance, some oxygen coming in as, and we got to be careful here because when I say oxygen, I'm referring to atomic oxygen, but we also have molecular oxygen. And so if I say oxygen, we have to distinguish whether I'm talking about atomic oxygen or molecular oxygen. But I'm talking about here atomic oxygen. So let's just assume that we have some oxygen coming in as water and oxygen molecule. So in this case we have an inlet of 100 moles H2O and 25 moles O2. So that's our inlet, and we want to know how many oxygen atoms are coming into our system. And so NO in is equal to 100 moles H2O. Got to pay attention to our units so we get them right, otherwise we may mess up, make mistakes, and that's 1 mole O per mole H2O plus 25 moles O2. and that's 2 moles of oxygen per mole O2. And this number here, this ratio, is just simply because every oxygen molecule has 2 oxygen atoms. So if we do this, coming in we have 150 moles of oxygen atom. And I could write out similar equations for oxygen atoms, or excuse me, for hydrogen atoms. I could write a hydrogen balance where for every mole of hydrogen, or every mole of water, we have 2 moles of hydrogen. For every mole of hydrogen molecule gas, we'll have 2 moles of atomic hydrogen. And the idea behind the atomic balance method is that we simply go ahead and write out our balances, figure out how much hydrogen atoms coming in, hydrogen atom leaving, oxygen atom in, oxygen atoms out, and we use the atomic balance equations to go ahead and solve for our species that are leaving our reactor. Sometimes, well, most of the time, probably the most common one we'll deal with is extent, but there are alternative ways, these 3 different ways that we can go ahead and solve a system, so we need to be aware of them in case some of these other methods may come in handy.